attendance form. Someone just copy and paste the attendance form. So today so we are going into the new chapter. Okay, I will divide this chapter into 2 weeks. Okay, so today we are covering some of them, and next week we'll cover the next part, and we can wrap it into weeks lah. Chapter 4. It's not too long like chapter 3. Okay, and chapter 4 is about flow in pipes. Okay. Okay, so there are few sub-chapters. Okay, the first one which we will learn today is the characteristics of laminar and turbulent flow in pipes and ducts. Okay, and the second, third, fourth ni they are together. Okay, so that's why I will touch this sub-chapter in second class or next week. Okay, no, next second class lah. So this week as well, this week as well. Okay, losses in piping system, piping networks involving losses, and lastly application of steady flow energy equation. Let me allow people count first. Okay, so for today we just we touch on the laminar and turbulent lah. Okay, 4.1 Okay. So introduction. Okay, liquid or gas, your fluid lah. Fluid can be liquid or gas. Flow through pipes or ducts is commonly used in heating and cooling applications and fluid distribution networks. So you have flow in a pipe. Okay, used for heating and cooling and also to distribute. Okay, macam oil and gas kan. So you have a huge network of fluid distribution underground. Okay, to distribute your oil lah. So that's one example. Or at home. Okay, if you kat home kat mana heating ni, kalau kat UK lah, kat UK ada heating system kan. So we have that heating system flowing inside our home, and we flow that the water, the hot water. Okay, macam-macam lagi lah and cooling pun boleh. Okay, so that fluid, okay, is whether liquid or gas, flow inside the pipe, usually forced by a fan or pump, and to make it flow through that pipe or duct, so you need to have a fan or pump lah, and so that's how the fluid flow inside the pipe or duct. Okay, we already touched this before when we learned in the Bernoulli equation. We said that any fluid flow in pipes, okay, will not the Bernoulli equation said, when you want to apply the Bernoulli equation, it must be the friction tak ada kan, maksudnya frictionless lah kan. But we know that in reality there is no such thing. There will always have a friction. The fluid flow with the pipe, okay, with the wall of the pipe will always generate a friction lah kan. Friction lah. Okay, so because of that friction, okay, in the fluid flow with the pipe, so you will get loss lah, the loss and pressure loss, pressure drop, and head loss during the flow of the fluid through the pipes and ducts. Okay, so that's why we need to calculate that loss. Before this, we assume when we do the chapter 3 Bernoulli equation, there is no losses. But in this chapter, in the reality, in this chapter 4, we know that there is a loss in that pipe. So we need to calculate that, and this chapter will teach you, will give you how we can calculate that, so that we have the real calculation of Bernoulli equation lah. Okay, so we need to calculate that pressure drop and then the head loss in the pipe, in the fluid pipes. Okay, so when we know the pressure drop, when we already calculate that pressure drop, so we know that how how much power that we need to supply the fan or pump to supply in our distribution network in order to flow the fluid, kan? So that's the purpose lah, to find the pressure drop or the loss, so that we know how much that the pumping power requirement. Because we use the fan or pump, so that pump we need to determine how many megawatt that we want to give in our pump to flow the fluid inside the pipe. Okay, so normally we have a circular pipe, so this is very common. Okay, in underneath or in your dekat sink ke ada pipe kan. So normally it's circular pipe, and sometimes it's a rectangular duct. Okay, why commonly is circular pipe? Because circular pipe can sustain higher pressure lah. Okay, so that's why we use circular pipe. Okay, and normally when we use the rectangular duct, we use it with the lower pressure. Okay, or they cannot sustain the higher pressure. Normally the circular one can sustain the large pressure difference. So that's introduction lah. So you have a fluid flow inside the pipe, and because the fluid flow has the friction, give you friction, so you have the pressure drop. So we need to calculate that pressure loss in order to give, in order to know what the pumping power requirement. Okay. All right. So in the pipe or in the duct, okay, the fluid can flow in two different region lah. One with laminar and one with turbulent. We already touched this a little bit in chapter 3. The laminar and turbulent, we differentiate what is laminar and what is turbulent. Okay, so this in chapter 4 we touch it again, because we need to calculate the fluid. We need to know the fluid whether it's flow with laminar or turbulent. Okay, we need to calculate that using the equation, what we call Reynolds number. We will see after this. Okay, so laminar flow, as you already know, it is orderly, kan? The layer of the fluid move in orderly manner, kan? It's very smooth. If you look at this example, the diagram, and they said here, this is the candle. Okay, if you look at the smoke of that candle, okay, or it says here from the cigarette, if you are a smoker, okay, I hope you are not. Okay, it's not good for your health. Okay, but let's say you see someone smoke a cigarette. Okay, when they exhale the smoke from their mouth, you can see the smoke. First is going out, is very smooth, and after that the smoke is not really smooth and have fluctuating, kan? The asap tu macam berkepul-kepul, kan? So that's the example of how you can differentiate laminar and turbulent. Okay, the first smooth region that comes up from their mouth, that's the laminar flow. After that, they change to the fluctuating, and that is the turbulent flow. Okay, if we can imagine that. Okay, so don't smoke. If you want to see this, I'm not encouraging you to smoke and to see this laminar and turbulent flows. Just for your example lah. Okay, so that is laminar and turbulent. We know this already. Laminar in orderly manner, and turbulent, the velocity, fluctuation velocity, and because of that, you have a very disorderly manner of that flow. Okay. Alright, and we can see this in a lab, in an experiment where you put some dye, okay, this purple dye, okay, through this pipe, okay, and this have a velocity, and you will see the dye will move very smooth, very orderly manner. Okay, so this is one example for laminar flow lah. Okay, But when you do for the turbulent flow, okay, when you inject the dye through this pipe and the velocity becomes higher, and the velocity higher, you can see the dye first it will move in the laminar flow. This one is this part is laminar, okay, still laminar. After that it change to the transition and then it will become turbulent. Okay, so this is how you can see the different behavior of laminar and also turbulent. Okay, I'm not sure we can of course we cannot do this. Okay, I'm not sure whether if we are not in this COVID, maybe we can do this experiment just to see, or you can Google from the YouTube. There's a lot of videos on how laminar and turbulent flow and the difference between them. Okay, so that is laminar and turbulent. Okay, so we observe this is from this from this experiment. Okay, we observe that the dye streak forms a straight and smooth line at low velocities. So this is a laminar, and then after that has bursts of fluctuation in the transitional regime and zigzags rapidly and disorderly when the flow becomes fully turbulent. So it will change from laminar transition. Kat sini transition lagi, dia kadang-kadang dia laminar, dia ada turbulent sikit. This is what we call the transition phase, and then after that is fully turbulent lah. Okay. So the conclusion he says here, the laminar smooth streamlines and highly ordered motion, turbulent the velocity fluctuations and highly disordered motion. The transition is the region between them, between laminar and the turbulent. Okay, but most flow inside a pipe distribution network or in practical, mostly we are dealing with turbulent lah, because the fluid flow very high in velocity. So that's why we normally accounted with the turbulent flow. Laminar flow ni very few, where you just because the velocity is very low and it's not helpful lah when in the piping network. We want the flow to be flow in high velocity not in low velocity. Okay, so that's why normally we encounter a turbulent flow. Okay, any questions so far? I think this is very straightforward lah. Laminar and turbulent. Okay, so in order to calculate this laminar and turbulent flow, we use what we call as Reynolds number. So Reynolds ni nama orang lah, Osborne Reynolds. I'm not sure where he came from. Okay, so the transition from laminar to turbulent depends on the geometry, the surface roughness, and the flow velocity, surface temperature, and type of fluid. So ini adalah faktor yang boleh menyebabkan perubahan laminar to turbulent. But in 1880, okay, this person Reynolds, Osborne Reynolds, discovered that the main thing that changed or the big factor of laminar to turbulent is the inertial force and the viscous force. Okay, so he found this, okay, in his discovery. Okay, so he found that the main factor is the inertial force and the viscous force. So that's why he introduced this equation to calculate the Reynolds number, the inertial force divided by the viscous force. And this Reynolds number is a dimensionless quantity. There is no unit. Okay, it's just a number, and that number will tells you whether that fluid flow is laminar or turbulent. Okay, so the inertial force is the velocity times the diameter. Okay, this diameter divided by viscous force, the viscosity. Okay, so this is the kinematic viscosity. Okay, and we know that kinematic viscosity is mu over rho, dynamic viscosity over density. So we can write this equation with this lah, rho times velocity times the diameter over mu, over the dynamic viscosity. Okay, because kinematic viscosity equal to mu over rho. Okay, so 1 over this is nu in Greek they say this nu so 1 over viscosity, the kinematic viscosity is rho terbalik lah, rho over mu lah. So that's why you can change this equation to this equation. Okay, so so inertial force is the force because of the inertia lah of the flow, and the flow is moving, so that will bring the inertial force. Okay, and the viscous force which oppose that inertial force. So with the viscous force yang akan bertentangan lah dengan flow of that fluid. Okay, so that's why if you have a higher number of Reynolds number, and if this Reynolds number is high, because this number it depends on the velocity velocity of the flow. Okay, that means the viscous force yang lawan this inertial force is very small, so that's why you have a higher Reynolds number. And when you have a higher Reynolds number, that means your flow is turbulent. Okay, we will see after this at what number that will tell us that the flow is turbulent, or what number this will tell us this is laminar. Okay, so in laminar flow, so the Reynolds number is low. Okay, and you have the inertial force, the velocity is moving very slow, so that's why the viscous force can oppose that inertial force. Okay, so that's why you get a very low Reynolds number lah. Okay, so this is equation, okay, that you will use to calculate the Reynolds number, and from that Reynolds number you can tell whether the flow is laminar and or turbulent. Okay, alright, so this is how they derive the equation. We don't need to know this, how we can derive the equation. Okay, we can just use the final derivative of equation. Okay, this one. Okay, or this one lah. If the question give you the rho and dynamic viscosity, so we use this one lah. Okay, if they give you the kinematic viscosity, so you can use this equation. Okay, so the Reynolds number can be viewed as the ratio of inertial forces to viscous forces acting on a fluid element, okay, as we have discussed before. Okay, so this is how we can know that the fluid is laminar and turbulent. It will depend on the value of the number, kan? So there is what we call as critical Reynolds number, RECR, critical Reynolds number. At this critical number, the Reynolds number will change to turbulent. Okay, will start to change. Okay, maybe it's not fully turbulent yet, but it start to change lah. Okay, so this is the number. Okay, 2300 for circular pipe. Okay, but this number will depends lah, will change, depends on the different geometry. So different geometry will have a different number lah. Okay, and flow condition and the velocity and everything. Okay, so we know at 2300, okay, the flow is no longer laminar. Okay, it start to change into the transition region, or we can say it start to go to turbulence flow. So this is the number lah. Okay, okay, and we know from the equation, okay, from this Reynolds equation, I wrote it here lah. So Reynolds number is equal to the rho times V times D over mu. Okay, so we have a diameter terms inside our Reynolds number. Okay, so we need to know the diameter of each the pipe lah. So if the pipe is circular, so what is the diameter of that circular pipe? If the duct is the rectangular duct, okay, this rectangular duct. Or if it's square, so it is a square duct. Okay, so we need to know. It will say to you what is the geometry of the pipe or the duct. Okay, because you need to find the D, the diameter of that pipe or duct. Okay, so this Reynolds number depends on this hydraulic diameter. We call this hydraulic diameter, okay, DH. Okay, and this hydraulic diameter we can find through this equation. Okay, 4 times area, okay, the area of that pipe or duct, divided by P. This P is the wetted perimeter. Okay, perimeter yang dibasahi. So if I can if we look from this example, okay, for flow through circular pipes, okay, this is the most common lah, circular pipes. The DH actually is D lah, diameter. The hydraulic diameter is the diameter. If you we can see from the equation, if 4 times the area is pi r squared or pi d squared over 4 over the weighted perimeter, and we know the perimeter of this circular pipe is pi times diameter kan. To find this perimeter, pi times d lah. This d diameter times pi, we will get this perimeter kan. Okay, so when you put this in the equation, you can cancel out the pi. Okay, you can cancel out the d, 1d, and you can cancel out the 4. So that's why it will leave back to the d lah. So that's why for circular is straightforward. The diameter is diameter. The hydraulic diameter for circular pipes is the diameter itself. Okay. But for the non-circular pipes, okay, for the non-circular pipe, you need to use this formula. Okay. Circular pipe pun benda sama juga, cuma it will always go back to the diameter lah. It's shown here. When you put in the equation, you will get the diameter, the hydraulic diameter same like your diameter for circular pipe. But for non-circular pipe, as this one, the square duct, rectangular duct or channel, the channel is open open. You can use this equation to find the hydraulic diameter. 4 times the area. Okay, the area of this is A times A, so that was A squared, over the perimeter. So you have this perimeter A plus A plus A plus A. So that's why you have a 4A, and this one we cancel out. Will give you the diameter, the hydraulic diameter for a square duct will equal to the A, this length lah, the length of this square. Okay, or the width, same lah, square length width sama kan. Okay, so this will equal to A, the D inside the equation, it will equal to the A for a square duct. Alright. But for rectangular duct, you will find again with the same equation. Okay, 4 times the area. So this in this rectangular duct, the length of the width and the height is not the same. Okay, so that's why it's A times B for the area. So 4 times A times B divide by the perimeter. This perimeter is equal to A plus A, B plus B. That's why they have 2A plus 2B. Because B plus B, A plus A. So that's why the perimeter is 2 in bracket A plus B, 2A plus 2B. And if you simplify this, it will give you 2AB over A plus B. So this is your hydraulic diameter for rectangular duct. Alright. Saya law dulu. Okay, can you just give him the attendance link? Again, from WhatsApp. Okay. Okay, so this is rectangular duct lah. And for channel, it's open shape. Okay, and because it says only hydraulic diameter, okay, and your this P is weighted perimeter. parameter yang kena dengan air. So we just take this length lah, A plus B plus A, and yang atas ni tak payahlah sebab this is not there is no parameter for this part what you call this open channel kan. So you have again P 4 times the area. So you have the area for this channel is A times B, okay, with the fluid lah, yang ada fluid je, okay, with the fluid, okay, 4 times A times B, so 4AB, divide by the weighted parameter A plus A, ni A juga kan, so will be 2A plus B, okay. So this your hydraulic diameter for channel, okay. So it will be different, okay, with different geometry. Okay, you have rectangular duct, you have channel, and you have square duct. Okay, so you need to know how to find the hydraulic diameter by using this equation. Okay, it's just easy lah. Hydraulic diameter equal to 4 times the area, okay, the cross-sectional area of the pipe divided by the weighted parameter. Okay, and for circular is just the D lah. Okay, the DH will equal to the D, the diameter. Right. Any question before I move on? Soalan?
No, sir.
No, sir.
No, sir.
Tak ada Okay. So we can move. So Reynolds number. Under most practical conditions, the flow in a circular pipe is laminar for the number below this number lah. We already touched this. Below 2300, we will call that flow, or that flow is in a laminar condition. Okay. So this laminar flow will below than the 2300. If you get, when you calculate the Reynolds number and you get more than 2300 but below 4000, okay, this is very important. Okay, it is not laminar flow and it is not fully turbulent flow. It is in the transition. Okay, so you can say it is in the transitional flow. Okay, between 2300 and 4000. Above that, above 4000. Okay, when you calculate the Reynolds flow, the Reynolds number using the equation rho times V times D over mu. Okay, when you calculate this number and you get more than 4000, so you know that the fluid is flow with the turbulence condition. That means very high, very fluctuating, have a disorderly manner lah. Okay. So this is very important lah. How we can note that the flow is laminar, transition, or turbulence. And like for example, this flow in your dye injection. Okay, you inject your dye at the beginning. Okay, the dye flowing with the laminar. Okay, and after that it moves in the transition. Okay, and above that, beyond that, we will move in fully turbulent flow lah. Okay. Alright. So this is apply lah. This you need to remember this. Okay. This critical Reynolds number is 2300. Okay. So below this is laminar, and beyond 4000 is turbulent, and between this number what we call is transition. Okay. Okay. So that is the first part lah of chapter 4, when we learn about laminar and turbulent and how we can calculate whether the fluid is laminar or turbulent. Okay. I will give some example of how we can use the Reynolds number to calculate lah. Okay. This chapter usually they combine lah. Normally you need to find the Reynolds number, okay, and then you will use that Reynolds number to find your losses in the pipe. Okay, but I will not teach you everything in one class. Okay, we will go one by one. Okay, So if you in the past paper, so you will see a question something like this lah. Okay, they ask you to find the losses in the piping system, and maybe they ask you to find what is the required pumping power of the pump. Okay, so to get to that answer, in the beginning you need to know first whether the flow is turbulent or laminar, because that number will will give you the friction factor. This we will touch later lah. Okay, so today just focus on how to calculate the Reynolds number first. Okay, so we will only answer part A lah, part A question question in this whole question. They say a water supply system for a building is shown in figure. So this is the water supply system. The flow rate of water being pumped is 10 liter per second. So they give you the Q. This is the Q. Again, your Q. I hope you still remember. And the volume flow rate. Okay. Through a 60 meter long and 0.15 diameter galvanized iron pipe. Okay, so this pipe, okay, is 60 meter long, and the diameter of that pipe is 0.15. So this is your diameter lah. And because this is a pipe, okay, and diameter, so we know it is a circular pipe. Okay. So they say the minor loss coefficient. So this we will touch this in the next class lah. About this minor loss and how we can calculate the losses. Okay, but now we want to focus on how we can on the Reynolds number first. Okay, in this one they ask you to determine the flow condition of water in pipe. Okay, this flow condition whether it's laminar or turbulent lah. So from this we can use our Reynolds number equation. Okay, is equal to rho times V times D over mu. Right? So we have the rho. So rho of this water is 1000. Okay, kilogram per meter cube. Okay. The velocity. So we need to find the velocity from the Q. Okay. So you can find the velocity from the volume flow rate. Okay. So they give you the Q 10 liter per second. So this Q we can change that in meter cube per second. Always remember you need to change back in the standard unit. Okay, 10 liter per second. Okay, second tu dah betul lah. So we need to change the liter lah. Okay, 1 liter equal to 0.001 meter cube kan. Okay, so this will give you the Q equal to 10 times 0.001 will be equal to 0.01 meter cube per second. Okay, so you can find your V, okay, from the continuity equation. So V will equal to 0.01 divided by the area. Okay, so they have the area for this galvanized iron pipe from the diameter. So this means the pipe is constant diameter lah. The cross sectional of the pipe is constant. There is no smaller pipe or whatever. Only same constant diameter. So 0.15 divided by 2, 0.075 squared. Okay, and this will give you the velocity lah of the flow. Squared 0.0 squared times pi and you will get 0.5 0.566 meter per second. Okay, you get your V, you get your rho, and the diameter is 0.15. So you have the diameter, and the dynamic viscosity. Oh, here, So they gave you the dynamic viscosity 1.31. Okay, so you can just plug in all the value inside your equation. So 1000 times V 0.566 times D, the D is 0.15 over 1.31 times 10 to the power of minus 3. Okay, and if you calculate this, it will give you 1000 times 0.566 times 0.15 divided by 1.31. So you get the answer is equal to 64,809. Okay, and this value is bigger than 4,000. So you know that this water, the flow condition of water in that pipe is turbulent. Because it is more than 4,000 here. Okay, that's how you use the Reynolds number in order to know that whether the water is flowing with laminar or turbulent. Okay, so that's one. Okay, another one example I show you here. So they give you the water with the rho and the dynamic viscosity, and this is the rho, the viscosity flows through a piping system shown in figure Q5. The pipes are made of wrought iron. The length and diameter of each pipe are given as, so there are two pipes, different pipes. So one with the length 60 meter with diameter 0.289, and the second one is 22 meter with diameter 0.194. Okay, so they gave you the Q again. The volume flow rate of water is 0.05 meter cube per second. So determine the Reynolds number and state the flow condition of water in each pipe. Okay, so you have pipe 1 and pipe 2 lah. Okay, so again Reynolds number equation, rho times V times D over mu. Okay, and you have everything, I guess. Okay, just you need to find the velocity lah. Okay, for pipe 1, the velocity for pipe 1 will equal to 0.05 divided by pi times 0.289 divided by 2, 0.1445 squared. Okay, so you will get the velocity equal to 0.05 divided by pi times 0.1445 squared. So you get 0.762, okay, meter per second. Okay, so that's your V1, and you can get your V2. Okay, V2 is V2 will equal to pipe for pipe 2. Okay, 0.05 divided by pi times 0.194 divided by 2. Okay, I use pi r square. Okay, if you want to use pi d square over 4, you also can do that. Just the same. Okay, so this will equal to 0.05 divided by pi times 0.097 square. So 1.69 meter per second. Okay, so you have your V2 and V1. So just plug in again in your Reynolds number equation. The rho is 1000 times V 0.762 times D. So the diameter of pipe 1 is 0.289. Again, the pipe is in the circular, okay, because they give you the diameter, so you don't need to find your hydraulic diameter. Divide by dynamic viscosity 1.0 times 10 power of minus 3. Okay, so you get your Reynolds number for part 1 is equal to 1000 times 0.762 times 0.289 divided by 1 power minus 3. So it's 22,000 0218. Okay, 218. So this is more than 4,000. So it is turbulent lah. Okay, turbulent. Similarly for pipe 2, you do the same. 1000 times the velocity 1.69 times the diameter of pipe 2 0.194 divided by dynamic viscosity minus 3. So this will give you 1000 times 1.69 times 0.194 over 1 times 10 to the minus 3. 32,000 or 327,860. Okay, so this is larger than that, so this is more than 4,000. So this also turbulent. Okay, as easy as that. Okay, just using the Reynolds number equation. Okay, any question?
Oh, sir.
Tak ada. Because this part is very easy lah. Because this only the starting point to solve. You see here there are a lot of question more friction. Because the thing is you want to find the losses. But first thing first, we need to find the flow, whether it's laminar or turbulent. Okay, sama jugalah dengan example ni. Okay, Reynolds number you can just ini pun circular juga. When they give you the diameter, okay, but this is in millimeter. Okay, just change back in meter, and they give you the Q. Okay, so this Q you need to change this Q in meter cube per second. Okay, so they give you in liter per minute. Okay, and you have your rho 1000, and you have your this is kinematic viscosity kan. Okay, so you just use the equation with the kinematic viscosity. Okay, is V times D over the kinematic viscosity. So they give you this, not dynamic viscosity kan. Okay, so velocity you can find from the continuity equation. Okay, Q over A. Okay, the A from the diameter pi r squared. You get the V. You get the V berapa? You plug in your equation. Your diameter is diameter in meter. Change this in the meter, and you have your kinematic viscosity. So you can get your Reynolds number, whether it is laminar or turbulent. So that's how you calculate that. Okay, that's why normally the pipe is circular lah, so that's easy. So you just use the diameter kan. But if the question gave you it is a duct, the duct, whether it's rectangular duct or square duct. Okay, so you need to find the diameter first lah, the diameter using the equation for A over P kan. Okay, so you need to find that diameter first. Okay, so that's only the difference lah between non-circular and circular pipe. But obviously commonly pipe is in circular shape. Okay. Okay, so this is losses in membrane system. I will not go in this part, okay, because if I go in this section, I will need to go for everything lah. Okay, that's why I leave this one in the second class. Okay, so for today's we just only focus on laminar and turbulent. and to find that you use the Reynolds number. Okay, any more question? Ada soalan apa-apa?
No.
Anything? Tak ada. So so we can end our class earlier lah. Okay, is it okay like that? Okay, I don't think I will touch the losses yet. Okay, like I said, if I touch on that subject, I will need to finish everything because it's related. Losses in the piping and the piping system. Okay, so that will cover in our next class. Okay, next Tuesday. Okay, and the next week we can do this tutorial lah on this chapter. Okay, alright. So that we can so today we can end our class earlier. Okay, don't forget your attendance form if you not fill up yet. Okay, and we meet again next Tuesday. Okay, tak ada kan? Boleh? Apa, tak ada soalan lagi kan?
Oh, sir.
No.
So with that, I think I end this class. Thank you for your attendance and Assalamualaikum warahmatullahi wabarakatuh.
Thank you, sir.
Waalaikumsalam. Thank you, sir.
Thank you, sir.
Thank you, sir.